Combustion control systems include air and fuel flow control. A combustion control system regulates the fuel and air input or the firing rate to the furnace in response to a load index. The demand for firing rate is, therefore, a demand for energy input in the system to match a withdrawal of energy at some point in the cycle. For boiler operations and control systems, variations in the boiler outlet steam pressure are often used as an index of an imbalance between fuel energy input and energy withdrawal in the output steam. A great variety of combustion control systems have been developed over the years to fit the needs of a particular application. Load demands, operating philosophy, plant layout, and types of firing must be considered. And in our case, it is a pulverized coal-fired boiler. It requires a more sophisticated combustion control, having several pulverizers. Each pulverizer supplies a group of burners that are located in an open or compartmented windbox. Primary and secondary air are admitted and controlled on a per pulverizer basis. Let us leave the details of this control strategy in our discussion later. This is a typical dual fuel firing strategy. You can try to relate or visualize what is happening in our actual plant setup. Let us discuss this diagram. Okay, a metering type control strategy for a boiler capable dual fuel firing simultaneously has to account for the total furnace heat input and different fuel and air ratios. The basic strategy of the boiler energy demand, establishing the total fuel demand to the boiler and fuel to air ratio on a boiler basis, is to be satisfied. Dual firing may include one or more of the following operating modes. One fuel in manual with the second fuel automatically following boiler energy demand. Another is one fuel in automatic with operator flow set point with second fuel automatically following boiler energy demand. And the third, both fuel automatically following boiler energy demand. If both fuels are following a boiler energy demand, then an operator adjustable fuel ratio setter determines the ratio of the fuel being fired. Unless both fuels are automated to follow the boiler energy demand, and the fuel ratio setter will track the actual fuel flow ratio. Airflow is to be cross-limited by the total fuel flow inputted into the furnace. When firing dual fuels simultaneously, the airflow demand is to be characterized based on the ratio of fuels being fired to establish the correct fuel to air ratio. When firing dual fuels simultaneously, the oxygen set point is computed based on the ratio of both fuels. These are the fuel flow control windows in the CRT or HMI, and most probably you are familiar with this. But somewhere in your brain, I'm sure, there is a question: how our control system manipulate the variables and maintain the process? And for the fuel flow control, isa-isay natin ang mga faceplates na yan mamaya. This is the original fuel flow control diagram ng Unit 1 and 2 APC, followed by Pag 3 fuel flow control diagrams. At katulad sa ibang modules, you can pause the video, put in full screen, and try to analyze or interpret these SAMA diagrams. Fuel flow control is designed to control the in-service coal feeders as well as the warm-up fuel oil flow. Under a low transient condition, the fuel control signal changes the coal and the fuel oil flows. However, it is always set to be below that of the airflow to prevent a fuel-rich mixture. The coal demand is determined by the difference between the total fuel demand signal and the actual fuel oil system when warm-up oil is in service. Likewise, the same applies to fuel oil demand. A bias logic signal is automatically set up between the two that looks at the fuel demand and the number of coal feeders and warm-up oil burners in service. This establishes the amount of change each flow, both coal and fuel oil, is controlled to. Do not be confused if you cannot see those things I've said in this diagram. We will discuss it on the next slide. Let us divide the fuel flow control into 4 subloops, namely the light oil control, coal feeder control, total coal control, and then the airflow, fuel flow, and spray. The light oil flow control diagram is illustrated in this figure. The fuel flow controls, monitors, and regulate the flow of light fuel oil and pulverized coal to the boiler. The feed rate of light oil and coal can be adjusted individually or together. Fuel oil feed rate is controlled by the light oil flow control valve. The light oil flow is measured and summed with the total coal flow to produce the total fuel flow. When the light oil burners or light oil valve is closed, a 0% signal is substituted into the control loop. The total fuel flow is compared to the total fuel demand. This creates an error signal or fuel flow deviation, which is processed through the proportional integral block to the light oil flow control valve. The light oil pressure is also compared to the minimum pressure, which is 15 kilograms per centimeter squared. If it is below the minimum, an error signal is processed through the controller. During startup, the controller contains 28% input signal. Startup is defined as less than 2 oil burners are in service. Now this is the coal feeder control diagram. The boiler input demand and the airflow are sent to the low signal selector. The lower signal is selected and used as the total fuel demand. This total fuel demand and the set value of mixed combustion rate are sent to another low signal selector. The mixed rate combustion setter allows the operator to set the ratio of coal and fuel oil. The lower signal is selected and multiplied by the total fuel demand. The resulting signal is summed with the total coal flow. The signal is compared to the total fuel demand to create an error signal. This error signal is sent or processed through the mill master setter. The mill master setter sends a process signal to all 5 of the coal feeder controls. Each coal feeder has a bias setter to allow the operator to adjust loading between the mills. And this is the total coal flow diagram. The coal feeder speeds are added together to give the actual total coal flow. For any feeders out of service, a zero signal is substituted. The total fuel flow value is compared to the megawatt demand signal. This results in a total fuel flow deviation signal which is processed through a PI block in the mill calorie setter. A value of 6,340 calories per kilogram of coal is divided into the mill calorie setter signal. The resulting value is multiplied by the actual coal flow to give the total coal flow demand signal. The process loop for the boiler fuel flow, airflow, and boiler spray are illustrated here. The boiler fuel flow, boiler airflow, and boiler spray signals are predictive, calculated signals based on actual megawatts, load target, load index, and the boiler input demand or the BID. The load target is compared to the megawatt signal demand. The resulting error signal is trimmed by the boiler input demand. This signal is multiplied by the load index signal, resulting in the final values for the boiler fuel flow, boiler air flow, and boiler spray signals. Now let us try to analyze the control logic behind these space plates, starting with the mixed combustion rate setter. By looking at the title, we surely get an idea of what this control sheet is all about. Look at those analog inputs at the top. These two are labeled. Therefore, you knew what the signal is. These 3 are unlabeled. And tracing back, it came from sheet 3.3.047, which are computed values and or value from ABALGEN. You knew what an ABALGEN was, right? These 2 are from sheet 3.3.006. They are from DBALGENs. And this one is from Millmaster Atom Manual Logic, sheet 3.3.119. This is a set point algorithm, divide and sum function, log BTC, which is a function of log with fixed limits, variable time constant, and tracking. And this is a transfer block that if on state will choose this input, in off is the other way around. Take note that we are trying to analyze the whole control sheet. That's why we are identifying each and every function. But if you are tracing a signal or trying to understand, let's say, a control loop, you don't have to do this. Just focus on a particular signal, where it came from, where it went, and how it acquired that value, considering the current conditions. Okay, this outputs goes to sheet 3.3.051, and the signal is eventually used in sheet 3.3.057, the mill master logic. So that's it. Mastering these basic skills plus the knowledge about the process or the control scheme, you will be capable of interpreting a more complex logic. How to master this? You have to practice. Let us proceed with the mill master control faceplate and discuss two associated control sheets. First is the auto manual logic for mill master. Well, this is a digital logic. It's just a combination of AND and OR functions with digital inputs on the left and the output on the right. I'm pretty sure that you can analyze this on your own. There are several sheets of this kind related to mill master. And this is the analog part. You can ignore this ABALGEN, although it may be used in this sheet or somewhere else. Let us focus on three distinct functions in this sheet: the PID controller, the mass station, and the balancer. You can ignore this text because it's just plain text, but it denotes informations about the function such as settings and parameters. Okay, this is a PID controller, but in this case, it is a proportional integral controller only. Why I say so? The derivative is set to 0, meaning there's no derivative action. If you may notice, the set point is set to 0, but the action is indirect, meaning the output should always be at maximum. And then the process variable, it came from sheet 3.3.054, and it is a computation from both fuels. This is a mass station algorithm. It interfaces a CRT-based soft manual auto station and an optional Ovation loop interface module card with the functional processor. There are three available modes: the auto, manual, and local. There are three types of this algorithm field depending on configuration. It may be auto manual station only. It can be Ovation loop interface module or a valve position module. Below it is the balancer. It monitors the modes of up to 16 downstream algorithms and perform a user-defined type of tracking when all the downstream algorithms are requesting the upstream algorithm to track. A special configuration of the balancer algorithms enables it to be used to balance the outputs of several downstream auto manual stations. By the way, we have available list of most commonly used function algorithms in our previous modules. We will not discuss all the faceplates because the module will be too long, but in the succeeding slides, I will show you the corresponding control sheets, each faceplates.